Okay, I'm gonna try and do this as systematically as possible, so skip a lot of things. The key thing about this carbonyl group is nucleophilic addition. That's the number one reaction we're dealing with, philic addition. And everything's gonna look the exact same way. We'll get to that later. Okay, so these are the functional groups that you need to deal with. Carbonyl functional groups. What is a carbonyl? A carbonyl basically is this guy here. And basically we're dealing with this group here. That is the carbonyl group, the C double bond O. Okay. So most of these functional groups down here should be familiar to you. The new stuff we're going to deal with is called ketals, acetals, and the imines. So they here, just take note that your acetal has two R groups. Your hemiacetal only has one, and the other one is a H. And just take note that for these acetals, right, they were derived from an aldehyde, as you can see here. So the H got to be present there, right? So your aldehyde came down to aldehyde derivatives. This is your ketone derivatives, so they came from a ketone. And same thing, just note that the ketal has your two R groups, and hemiketal only has one. Okay, and because you took this from a ketone, this is not going to be this group here is not going to be a hydrogen. It's going to be whatever carbon was there. Okay. Imines are also derived from carbonyl compounds, aldehyde and ketone, but it's just that same thing, that you will see that if it's like that, then this obviously came from an aldehyde, right? So this was an aldehyde derivative, and then the other one would be a ketone derivative. Okay, this would be ketone derivative. Same thing for the enamine, the same logic, so I'm not going to repeat that. But just note the difference between the imine and the enamine in terms of this imine, the bond is here, enamine, it is here. We will get on to what that means, but you can remember it for now as this ene, right, is associated with the double bond. Okay, so it's associated with this double bond. Okay, and your amine bit is associated with the fact that this NH is amine. Okay, next thing, okay, so bonding in carbon, for the bonding in the carbonyl group, you have to understand that the carbon is fucking electron deficient because of basically because this oxygen is very electronegative. So it will do shit. It will take away the electron density from the carbon by resonance, and so what you will get is something like that. And so because you can put this negative charge here, right, that means that by resonance, right, we can kind of prove that basically for resonance, if you can prove by these arrow pushing that you can get a plus charge down here, and a minus charge up there, then that's how you justify that whether or not an atom in a molecule is electron deficient or electron rich. Because if you can concentrate electron density onto that carbon, right, or that atom, basically you are showing that why it is electron rich, and we've just done that. Okay. Because so because of that, right, because of this resonance structure, that means that this carbon is very electron deficient. Okay, and we're gonna make it even more electron deficient when we do our reactions. It is possible for this to happen. Remember, the oxygen has two lone pairs. One of the if you have stuff in like acid in a solution, this lone pair, right, can actually just grab the H, and then that happens. Let me just move this out a bit, out of the way, and move that up here. Okay, that makes that happen. And so if this was already like, if up here, like, you already had the electron density pushed towards the oxygen here, then when the oxygen is even more electron hungry because it's plus, right? So the electron density will try and shift up there. Then that means that the carbon is even more, this carbon will be even more electron deficient. So I'll just put it as that. And then that will make it even more susceptible to a nucleophilic attack. So let's say it was like that. Then yeah, definitely you'll have a nucleophile come in and attack like that. And you will form something like that. Right. Which is interesting, right? I'm just gonna cut that out. Redraw it. Right. And that's interesting because now we've just formed the first step of our ketal formation. So this is actually a hemi-ketal. But anyway, that's just for you to understand. Right, okay, so the next thing, yeah, this slide is just, she wants you to just see that this is like that. So this pi bond is shaped like that. Your pi bond is just your attraction between the p orbitals like that. So those are the pi bonds. The sigma bonds are similar, right? You have an sp3 hybridized, sorry, you have an sp2 hybridized carbon, so that's down there. And by right, the orbitals are supposed to be drawn like that. We'll draw them like that. So each of those sp3 would be like that, right? Anyway, and then your oxygen would have, your oxygen also has something like that, which we're gonna just represent like that. These are your lone pairs. This is your sigma bond. Okay, sigma bond. And yeah, so actually your sigma bonds should be a bit bigger, just so I can show the overlap between the H atoms. So that is a sigma bond, that is a sigma bond. So that's all for this slide. Okay, SN2 versus nucleophilic substitution at the carbonyl. Okay, so basically this slide is just trying to show you that the reactivity of this carbon is different from the reactivity at this carbon. So what you will get here, right, is SN2. Yeah, SN2. versus nucleophilic substitution. Okay, so here what you will get is a direct attack on the carbon like that, and then that happens, and then you end up with that, right? Because it's in color, I'm gonna draw it with the carbons, sorry, with the color that they drew it, right? So that's the reaction that you will get from there. Whereas for what we get here, right, you will end up with this mechanism, which is different, and it is let me just draw what you get first, and then we'll get back to this. Okay, oops. Did that happen? Yes. So this is one of the... Oh, sorry, this is not... yeah, this is nucleophilic substitution at a carbonyl. So what is different? So this was... So why did it have to happen for our carbonyl? Why did it have to happen this way? Right? Okay, so I'm just going to draw it out like that. N sub at CO, different. Why? So, because, the answer is because, and I will write it in red, the pi bond is weaker than the sigma bond. So you got to break that pi bond first. Because there's the lowest EA to break. So you must, so that's why. So literally, the breaking of this pi bond, right, which I'm going to zoom in for so I can highlight the exact thing, right? The breaking of this pi bond is the most favorable thing, and so therefore you will break that pi bond when you supply energy to it. Whereas for your SN2 case, right, there is no pi bond to break, so you will have to, no choice but to break a sigma bond, which is what you're doing. So here, no pi bond. Okay, that was horrible writing. No pi bonds here, so you have no choice but to break sigma bonds. And in that sense, that's why this reaction for this intermediate also needs to, I guess that's also why you need that nucleophile to approach as well, right? Because if not, it's hard for that SN2 for that bond to break itself, but that's not the focus here. So the key thing here, this is the important part of this slide. Okay, next. Nucleophilic attack at a carbonyl, why a tetrahedral intermediate? Okay, so you got to remember that this thing is planar, right? So this, the LUMO of this is a pi star. So when do you have a LUMO, right? Is when the orbitals, remember, when the orbitals line up in antiphase, and so that's what it looks like. These things are in antiphase or out of phase. I don't know what they call it, but whatever. Okay, so your electrons in your nucleophile will have this thing, right? I'm gonna draw that as a non-colored, right? and this, and so what happens is that this lone pair, which is what I'm representing by this, right, is going to deposit into your anti-bonding MO. Okay, so this is the sorry, no, that's not the bonding MO, because you're not bonded to anything. But yeah, so this is an anti-bonding MO that your electrons will jump into. When that happens, you will then have this go into these electrons here will go into the anti-bonding orbital of oxygen, which is what happens, which I'm going to draw in red. And then here, what you will get is that exactly that sigma bond, right? And that's what happens. So yeah, just to show the what happens here, right? This is the bonding MOs, and then this is what ends. Just to show how the electron density is kind of concentrated towards the oxygen, to show that we have this, right? I'm just gonna draw it as such. Okay, so that's what it looks like, because oxygen is more electronegative, and so you are